Thank you all so much for continuing to come to these Martinis and Lights events. I see a lot of faces that I've seen before and actually a lot of new faces tonight, which we love to see. I hope you all enjoy yourself and our talk tonight. It's my honor tonight to introduce our speaker, Craig Marquardt. So I'm going to go ahead and tell you a little bit about him. Craig is an award-winning architect and lighting designer with 35 years of experience in architecture and lighting design. Craig studied architecture at Mount Hood College, which led to his first position at Skidmore, Owings, and Merrill Architects. He has also served as the Dean of Architecture and Planning at the Massachusetts Institute of Technology. Craig founded his own architectural design firm and in 1992 specializing in high-rise buildings, museums, airports, and public art lighting projects. In 2008, Craig joined us here at Acuity Brands as Director of New Products and Development, where he has helped to produce several solid-state lighting products. Would you all please help me in joining Craig?
Okay, for those of you that have been a part of the Thursday night Martinis and Lights, you know that I always begin it with a toast. Okay? I wasn't quite as creative this time, but I do think that we do need a toast. Let's all raise our glass to Thursday night because it's time for Martinis and Lights.
Well, welcome. Can everybody hear me okay? Yes. Good. I want to make one clarification. I wasn't the Dean of Architecture at Massachusetts. I worked for the Dean of Architecture at Massachusetts. Just a brief story. When I was still in college and I got approached by Skidmore, Owings and Merrill to come to work for them. And I said yes. And first day on the job, I walked in there and sit in the office for hours and hours. I'm starting to get worried. And finally, a guy came out and said, "There's your office right over there, and that's who you're working for." And it was this really little old guy. And I'm like, "What in the world?" And I was kind of getting freaked out. And I looked and I'm like, man, for some reason he looks familiar to me. Well, it was Pietro Belushi, so he is kind of the godfather of the high-rise building. He's the one that actually developed the modern-day high-rise that transitioned from brick and wood to steel and aluminum and glass clad. So that's when my education really started. Really I learned a lot about how you interact materials, site form, material, and illumination is what they really taught me. And that just kind of led me into more and more being more focused on being a lighting designer, not an architect. So anyway, today we're going to talk a little bit about technology, where it is today. 10 years ago, I was at Light Fair. I think it was Light Fair here at the Javits Center. And I was walking around and I seen some of the first LED products in the industry. And I seen a lot of my customers that I've been working with all these years. And I've seen some fellow architects and engineers I work with, and they all looked kind of baffled and confused as well as I did. I was looking at some of this product, I'm trying to think to myself as a lighting designer and an architect, why in the world would I want to specify a 2x4 troffer with 500 LEDs with no lens on, just sticking straight down? I tried to think to myself, I've strived so hard to design things that didn't have glare and that didn't clash with the architecture. And then here's somebody that spent an awful lot of money to buy a booth in Light Fair, and they're showing this LED light fixture, and it was like, wow. And then when I started really looking into it, I could see the automotive industry, they were 10 years already advanced over the architectural industry in LED, and they were really striving forward with this technology, and they were doing quite well with it. Almost every vehicle was going LED. And so I kind of knew that, the writing was on the wall and LED was coming. And me owning my own lighting design firm in Portland and Seattle, I figured that I had to learn this technology, otherwise I was going to go right out the door with other technology. So I started consulting with the automotive industry. The automotive industry really taught me about some really attributes on LEDs and what they were doing with it and how they were getting it to survive, especially in a really harsh condition. In a building, we're not like going over the Tetons and down the other side and going through all these thermal changes, you know, so they really had things figured out. So 5 years ago, I got a call from Acuity Brands Lighting, and they said they needed somebody to transition lighting design, application, and the technology to how we can apply it to architecture. And they picked me, and which I'm grateful, because I've been having a great time doing it, and the technology is just fantastic. Some of the things that are happening just in the last few months that you'll get to see maybe in a couple of years is just mind-boggling. But anyway, so the last 5 years I've been developing a lot of the both indoor and outdoor products for Acuity Brands. Most of the outdoor stuff that you see, I'm working with the optical engineering department actually report to me and get a chance to work with these scientists, and I interact with them in the sense of how we apply this high technology to everyday application. And so some of the slides that I got here today will lead up to those applications. But first of all, we'll go through some of that previous technology and get to understand what really LED is. When I first learned this, I was really shocked to find out that actually General Electric developed the LED in 1962. Some of you probably already know that, but to me, you know, the LED was way in advance of the HID technology. What's interesting with that, it wasn't until 1990 that the LED, finally Nichia developed the blue LED. That was the missing link to creating white light. And the reason that they couldn't go any farther with that, because all they had was red and blue, and they, you know, who would want, you know, your buildings red and green, not blue, sorry. Who would want to, you know, live under those kind of conditions? But from the 90s, the technology has just taken off like a spaceship. The amount of work that they have developed into bringing this little tiny dye chip to create so much light is just mind-boggling. This slide here really represents Tier 1 and a few of the Tier 2 LED manufacturers in the country, or in the world. Outside of everybody that you see up there, question it, because they probably are not legal to sell white light in the United States. All these guys are. A few other ones, a few Tier 3 ones that are not up there. The reason I didn't show the Tier 3 stuff is because they really can't manufacture enough LEDs to support a big company like Acuity Brands or other big manufacturers. We're very concerned that when somebody buys our product that they can get it on time, and we don't want to say, well, it's going to be an extra 3 months because we can't get LEDs. It's one thing we don't want to do. The part that is really interesting up here is Nichia, who owns the patent for the blue chip. They also own like 80% of the phosphor mines in the world. So in the early phases of this whole LED architectural technology, there was a lot of IP patent struggles amongst all of them. They were suing each other like crazy. And it wasn't really doing the industry any good. And one of the reasons that we've seen a lot of high prices in LED products is because of all those struggles. Well, finally, they got their act together, they had a group hug, and they said they basically cross-licensed all their products, for pretty much all their stuff, so that, in fact, when you see sometimes you buy like a Samsung flat screen TV, sometimes you might get Philips LEDs in it. They make so many LEDs, millions of them, the small chips, that they actually run out. And one of the reasons why they had to make up and quit all this nonsense is that they wanted to sell TVs and they had to buy LED structures from other people. And so they finally did that. Good news to us is that we're more integrated to where we can use any of those products. And, you know, I mean, Our company's not called Philips, or it's not called Cree. Our products are designed to use any of those LEDs. So in fact, if we ever have a supply problem, we can easily deviate and go to another LED and quickly move forward without any kind of hiccups. The LED itself this is a discrete LED, so this is the first LED that came out. This is the small chip. Pretty simple. I mean, it's just a circuit board. The black structure that you see is a substrate. It's made out of ceramic. The dye chip, or the LED dye, which is the epitaxy that they grow, and they cut up into little dye chips, and they bond or solder to the substrate, and then you have a lens. And you got two types of lenses. We typically see mostly the silicone lenses. There's a few manufacturers out there that are still using glass lenses, but there's some interesting facts regarding the silicone versus the glass. You're looking at, with the dye chip up there, the epitaxy, that's the blue chip. It's blue. In other words, if you took most LEDs and you knocked off the lens, it's going to be a blue LED. What they do is they mix the phosphor inside the silicone lens, and then they injection mold that lens right over the top of the LED, and that's how they convert from blue to white. Now in the case of a glass lens, they can't mix the phosphor in the glass, so what they do is they dope the top of the epitaxy with phosphor. There's some issues related to that, and you might have seen some of them where you'll see like a styration of color, like if you had a wall light or something that was putting a scallop on the wall, you might see some yellow and you might see some other ranges in there. A lot of times that's from light leaking out because they couldn't get all that phosphor on top of that epitaxy. And it would leak out into other, it would refract into other colors. Now this is the new guy on the block. This is the COB, it's chip on board. It's just a big LED. It's the same structure as the discrete LED, but if you look at that up there, you can see, maybe not from the back row, I sure couldn't, but there's a bunch of little dots in there. What you're looking at on that particular one, I think, is 100 LEDs, separate dye chips, all in one little yoke. And with this, all you do is you just buy the chip, you bolt it to a heat sink, you solder two wires on it, and hook it to your driver, and you're off and running. It makes manufacturing pretty simple, but there's just more to it than that regarding how you could actually structure this. So we started looking at some advantages, disadvantages, whether it's discrete LEDs or whether it's a COB. And in this case here, you're looking at COB on the left, which you kind of look at the structure of the reflector compared to the same lumen output. So you're looking at 3,000 lumens on the left, you're looking at 3,000 lumens on the right, which is discrete. The COB offers a much smaller luminous area than the discretes, because we can't push all the discrete LEDs together because the optics start crowding into each other, and then the efficiency starts dropping. So some of this is attributed not only that the LED manufacturers finally made up and quit suing each other, and the prices start coming down and they're getting a lot better at actually manufacturing that, but because we can actually make the luminous area smaller, these we make the fixtures smaller, luminaire smaller, so costs are falling because of some of this technology. We use both technologies, and I'll explain in another slide coming up here. The bottom one, which is kind of interesting, those are the flat screen TV LEDs. Those are the small, low power LEDs, quarter watt, 1/10 watt, half watt type of LEDs. We use those type of LEDs, and it's a really interesting circuit board. That circuit board we designed so that it's got copper on the back, it's got copper on the front, it's a two-sided board, and then it's got the LEDs on it. All you got to do is just slap it on a piece of sheet metal, and so the heat comes out of the face of the board, and the heat goes out of the back of the board. You don't need a heat sink for it other than just a piece of sheet metal. Some really good technologies that we developed. You'll see that's a foot-long board, so it's 1,200 lumens, roughly about what a fluorescent strip is. So you'll see a lot of that kind of a product put inside of troffers and strips. If anybody's got any questions, just shout them out. So some new advancements in materials. As LED technology kept growing and growing, and we became producing more lumens and creating more thermal within the luminaire, we started bumping up against other technology problems, such as acrylic and polycarbonate. In this case here, we've got the upper left of the white light engine there. That's got a polycarbonate lens in it. About the maximum we're going to get out of that structure is about 3,000 lumens. Before the what we call the radiation flux, the light that comes right out of that LED is producing heat and energy and overtaxing the structure of the LED. Be aware, as a specifier, there's a lot of manufacturers out there that use acrylic no matter what. And after a while, if you just keep radiating that structure over and over and over again, it'll start crazing and start turning color, and your lumen output start falling and eventually could potentially come apart. Structure on the right, the reflector on the right, that's polycarbonate as well, but that's a COB reflector. That's plastic that's covered with chrome. There's so much flux radiation coming out of that LED that you're not going to get any more lumens out of that package, but about that size. You'll see some manufacturers go to, and we do the same, we go to an aluminum reflector. We can handle the thermals a little bit better, but you just can't bend the aluminum in the corners as well as you can mold pieces, so you end up losing a little bit in performance. Question?
How do you know when you get acrylic versus polycarbonate?
One thing for sure is you need to ask the manufacturer. You need to be straight up with it regarding that. The question was, how would you know the difference between acrylic PMMA or polycarbonate PC? And there's a couple of ways that you can do that by burning it. There's different colors that come off. You can tell, PC creates one color of smoke versus PMMA. Those are the kind of things, but I don't recommend doing burning in your life picture. One thing to do is ask your manufacturer. When you're looking at this and you look at their spec sheets and you look at the lumen output, you might want to question them, because we see this over and over where people are just driving the LEDs as hard as they can and they're pushing that radiation flux through there. Acuity brands, we want to sell light fixtures, we don't want to warranty them. And so we go through painstaking validation and design so that we're not warranting these light fixtures. We don't want them coming back. We want them to last the life of that fixture. So, and some manufacturers, they just want a quick turn on the product. So you really have to watch that. The new development, some of you probably have heard of a company called Hall of Fame Lighting, which is very famous for glass. The glass optic there, my guy's been working on this for about a year. And typically, Hall of Fame glass is big, and if you've ever toured that facility, it's unbelievable. The size of the furnace is as big as this room. And they typically make gigantic optics. So when we actually went to those guys that have been working there for 30, 40, and 50 years and said, I want to make an optic this big, they thought I was crazy. And so they worked with us for about a year, and we developed some tooling and everything to get that optic over a COB and not have to worry about the radiation flux and crazing, dirt depreciation. So we've got really good outer structure that can be outdoors and maintain really good lifetime dirt depreciation quality. Also on that, there's just a ton of patents and IP associated to a bunch of other development that we're doing, where we're actually mixing and co-molding glass and silicone together to actually increase the performance. But right now, that glass and COA combination is about as high as we're going to get in technology today as far as lumens per watt delivery. It's an excellent subject. Also on that, when you look at this outer structure of that, and we're going to get into the glare here in a minute. When you look at that outer structure, and then when you look at the reflector, the whole outer structure of that glass is going to glow because we put a little bit of treatment in it. So you don't have that point source like you do with metal halide or like you do with the direct radiation of a COB. So there's a huge quality difference in glare difference between this type of an optic and just open structure. There's some of the, just a pick, I mean 100 years ago, the borosilicate glass versus this high-tech thing today that with the COB and reflectors and refractors and TIR that's happening in the optics there. So, has anybody heard the term binning? Has anybody come in there and talked about binning? This slide is the one responsible for all the problems in the LED technology. This is the culprit that was dropped in 2009. This was 70%, the LED costs were 70% of our luminaire costs because of this manufacturing process. Okay, what's happening here is the manufacturer is building one LED, and he starts it started this conveyor belt, and when it ends at the conveyor belt, they turn it on. And in 2009, that LED was either going to be 39 lumens or 114 lumens. That's not very good quality control. And 80% of that was their sweet spot. In other words, they were getting 80% of them that were pretty consistent. They were throwing away 20%. I mean, can you imagine going to Ford or Chevrolet and say you got to throw away 20% of your vehicles after you got them manufactured? Well, what they did is they just put the cost right back onto us as manufacturers, and that was what was driving that cost up. What we were seeing early on in these phases is some manufacturers, some of the unscrupulous ones, they would buy the whole bin structure. And then the LED manufacturer would say, oh, well, we'll sell you that real cheap. You know, but the problem is that when you have 100 LEDs in a light fixture, you could have one that's 39 lumens and the one next to it or a few positions over is 114. It's going to kind of look like it's burned out. And some of that early technology, we've seen tons of that where guys would come in and say, yeah, I've got a $100 light fixture here. You don't want to use those guys over there because they're selling for $200 to $300. But they wouldn't last because you were really buying poor quality LEDs. After 2009, that's what the binning structure looks like. They finally, the manufacturers have I mean, if you can imagine, you have to look at the epitax here, the dye chip under a microscope to really see how big it is. It's pretty small. If you can imagine dicing that up and making 1 million of them all the same, pretty tough. And that's where that problem was coming, is how they were bonding the LED to the substrate, getting the thermal through it, and then the size of the substrate varied so much. They have figured it out to where there's virtually hardly any more product that they throw away. The cost of the LED started just really, really dropping, and that's where you're seeing some of the LED costs coming down and fixture costs coming down. Costs on some products now are getting close to what HID technology was. In fact, it's like a no-brainer. It's like, why would you even want to use HID when you can buy it for this price anymore? This is an optical philosophy that I hope none of us really want to take as an optical designer. There's a lot of LED luminaire manufacturers that take this stance in optical design. And this is tarmac light. This is just a shot that we took at an airport lighting tarmacs. Some manufacturers don't have a real good depth in optical engineering and design. So what they do is they take the LED and they point it to what distribution they want. And then they take another LED and they point it to another spot and another spot and another spot. Just like that, what that fixture shows. The problem that you're going to get is that nothing's perfect in this industry at all. And you're going to get LED failures. And one thing that Acuity Brands has always been concerned about in a scenario like this, where you've got these reflectors, potentially you could have a burnout in a complete zone in your target, like right in the middle of a high conflict area in the sidewalk that's going to be dark. And then you've got high brightness here and zero brightness here. You've got contrast ratio that's huge. The last place that we want to be is involved in a lawsuit where wow, you know, your light fixture did great everywhere else, but right where we needed the light, there was no light. So we stay away from that type of philosophy, although it's easy to design a light fixture. And, you know, I mean, sometimes I think to myself, man, if we just do that, we could solve this problem. But, you know, we're not going to go there. We're going to spend all of our energy is really spent on developing an optic that does the entire job, one optic. So the optic next to it does the same thing. And so if you have 100 LEDs in a light fixture and you lose an LED, you're only losing 1/100th of a foot candle. You really can't tell that much. Here's some examples of what I'm talking about. There's some other issues related to this. You can see the luminous area. Both those fixtures are the same lumen output. They're identical. Same distribution, same lumen output. Except the one on the right, where our luminous area is like 1.5 feet by 1 foot, and the one on the left, that is like more like HIE. But as you move with the fixture on the left, the source or the image moves with you. And as it transitions through different optical distribution characters, it's like being on stage and somebody clicking cameras at you. You get kinetic flash. So as you drive down the road and you see fixtures that have this kind of optical distribution in it, you're going to see this twinkling and flash. It's kind of annoying. We're a little concerned about, you know, like creating disturbance in your ability to see your task. We'll talk a little bit now about site form, materials, and illumination. This is the fundamental part of the architectural portion where we have taken this fundamental and carried it into our optical distributions and how we form it into applications. Now I've got some samples, you know, some early on buildings. This is one of the first high-rise buildings I designed at SLM under Pietro Blucci and Jim Christensen. When we got this site, Pietro said, well, you know, what's our site? Well, there's no other buildings around it, so the site was the sky. We were competing with the sky in this case here. The form, because we were not competing, it was just this big mammoth right out in the middle of nowhere. We ended up creating building diamond shapes, so at least 50% of the view, it looked pretty thin. So there's kind of the form. And also when you rub your hand across the face of the building, you go from glass to granite, it's smooth. There's no mullions, there's no setbacks or anything. So as the sunlight hits it, it bathes the entire building and there's no transition at all. And the materials, we use Spanish marble and pink glass to create this. And the reason we did that, the Spanish marble that we picked was really hard, so we polish it, and it had a very good reflectance value, not as good as glass, but it was very high. The result is, when we had daylight with it, depending on the view you have of the building, sometimes the building took on a completely different shape, like a chameleon. It could come in and out of that. This inspiration really is where we started thinking about how we could develop optics that interact, or how the lighting designer can take these optics and interact it to a building and a site. There's some different pictures under different conditions. It's interesting how it reacts. And today's technology, like I said earlier, there's projects where it just makes it's a no-brainer to do it. This is one. 120 feet. I did the lighting design for this building with another lighting designer in 1980 or something like that. And it was metal halide then. And yes, I did get to go up in there, and it was fun to me, but most people, not too fun. Carrying it, getting up there to maintain that is just absolutely crazy. Today, if you have a project, I would just specify LED because it's going to be up there forever, and you don't have to get people up there to get hurt or anything like that. Here's another scenario of very early on metal halide technology. In this case here, using color filters. Color filters only lasted 30 days. So every 30 days had to shut 2 lanes of the bridge down and change the color filters out, change the color, and that went on for 20 years. And a lot of traffic jams for many, many years. Until it was 10 years ago, they contacted us again, got to light the project again, which tells me a little bit about my age. In this case, we used LED. LED in very early technology. Although it was really fun and cool and everything at the time, and real expensive. Unbelievable amount of cost to buy those fixtures. But one thing you'll notice is that the distribution is very tight. Early on, the LED technology did not really understand the optical, the implications of what optics could do. But what ultimately happened here, and the reason why I show this is that, it started to engage more people into architecture and lighting. The LED technology did, because prior to that, nobody really cared other than, oh look, the bridge changed colors. Now people, because they understand, they do a radio program every 30 days and they have a contest, and that person gets to change the colors on the bridge, for the next 30 days. So now all of a sudden you got a community involved where we've never had. I've never seen that in the industry so much, where people get involved with this technology. Another project very similar, in the mid-80s, we lit a bridge using Tivoli low voltage lighting. A lot of it was like 2.5 miles of this stuff. And it survived until around 2004, and then we ended up putting metal halide and high pressure sodium on it. And then last year, a Percent for Art project, not involved with me or anything like that, but Percent for Art, the artist ended up selecting the bridge and installing LED lighting on the bridge that interacts with cars going across it. And, I don't know how the State Department allowed that. Anyway, there's a lot of stuff happening on the bridge, but it's really becoming much and much more dynamic in how people get inspired by architecture and lighting. And these are photos that I just took off the internet just recently. Question?
I just want to know where the location is.
The bridges, those 3 shots, the bridges and the Convention Center Spire in Portland, Oregon. I took these off the internet. And it was amazing to me. There were thousands of photos of people, and there was even one where a guy had his arm tattooed with the building on it. And in my entire career, I've never seen the interaction of how people react and be much more engaged to architecture and lighting ever. And I have no idea why the guy that took the one on the left. I've seen the movie, I like it, but I don't understand now. I figured that one out yet. So. But it was just really interesting. Obviously, it inspired an artist to paint light and bridges and everything. So all that information coming at us has really brought us to tailored lighting. And so we started thinking, like, with tailored lighting, let's develop our optical distributions so that the lighting designers have several choices, like an artist, a palette, and you can start taking all these different shapes and sizes and start filling out and tailoring the lighting design of projects. You can see some of the distributions in nomenclature. We call them 1 short, 2 short. We have roadways and all sorts of different distributions. Here's some ISO plots. You get an idea of, really the shapes and the forms of all those. And then I turn the ISO plots on. That's really kind of the meat and potato as a lighting designer when you start looking at what that footprint is and how you can fit it like a jigsaw puzzle onto these projects. When you have, coming from the West Coast, where a lot of my work was done, had to deal with leads and Title 24. The green lines around the site represent light trespassing. So at the property line with leads and Title 24, I believe, back then, I'm going to think back, I think it was like 1/10 of a foot candle at the property line. And then out at 15 feet off the property line, it was 0.01 foot candles. So if there was a red in any of those green areas, that means that we violated. I got approached by a friend architect that was doing a LEEDs project. They were going after the highest LEEDs project that they could in Los Angeles at the time. And they were specifying a tier 1 lighting manufacturer. And that was their layout. And they couldn't meet the foot candle requirements. Primarily because they offered just your standard type 2, type 3, and type 4 distributions. When you go to tailor these projects, you can deliver, in this case, much more light. And in this case here, we saved them 2 poles and 3 luminaires, which is substantially a lot of savings, and we saved them a few bits of wattage as well. But 1,496 watts for an entire pretty big size lot is unbelievable. It was around a 2.5 candle average, so pretty high, very low voltage. These are just some simulation applications where you see the uniformities, and that was the key part of developing these optics and distributions, and as a lighting designer to look for. Okay, and the uniformities are key. For example, we have a customer that had parking lots all over the world, and they have a 5 foot candle average, pretty high, and they said, come on out, bring your fixtures, install, we'll give you this lot, and we hit the 5 foot candles, and they walked out and said, wow, there's just way too much light here. There's like way more than what we had with HID. But we showed them the foot candle reader. It was 5 foot candle average. And they're like, well, we don't need that much light. Well, yeah, because with HID, we had a nadir dump. We just dumped all that light straight down on the pole. We had all these uniformity ratio problems that to get the average up, you just had to keep jacking up the light level under the pole to bump the average, and then you have all these dark spots. So they came back, a national chain, they came back and said, let's move our foot candle average from 5 foot candles down to 2 foot candle average. But let's really maintain what the minimums are. And let's look at those minimums and make sure that we don't go below a certain threshold on the minimums. That was the key to reducing a huge amount of energy, better carbon footprint for projects, and that was our driving factor of when we developed these optics, that we created a palette so that you could use them and click them together essentially using software programs to maintain those uniformities. This is a real picture of a scenario. This is actually our PME buildings where I work. Those 2 pictures were taken 3 nights apart. You see a big difference in uniformities. Key factor is here, the HID was 0.9 minimum, and the LED was 1.4 minimum. So we really filled in a lot of those areas. You start looking at the trees, as lighting designers and architects, the cutoff was the same in both fixtures. Except with HID, we couldn't control all that radiation flux just dropping straight down below the pole. Now here's an interesting scenario. We see this every day. When I started in lighting, first job I had, I was in high school. I knew I wanted to be an architect. And across the street from the high school is an electrical engineering firm. An architect friend said, go over there and get a summertime job, right? And I walked in there, I got a job. And The guy said, okay, Craig, this is your first job. You're going to do a lighting layout in a parking lot. Go to the Guardco catalog. In the back of the Guardco catalog is a bunch of flimsy ISO plot distributions. And they were the only ones at the time that did that. And this was in the late 70s. And you take those out, and they're just scale, like, 1 inch equals 40 feet, and all this kind of stuff. You pull those out, and you Xerox, 20 of them or whatever, and you cut them out, and you paste them on drawings. And you overlap them, and that's how you did. We didn't have visuals then. I mean, big glory for thinking about it. Yes. That's how we did it. In this case, I would have deemed those two isoplots equal. And today, we're seeing it equal today. We're seeing reps come in and say, listen, mine's equal, they look good. And then, we go, okay, proved equal. They're far from equal. There's one 67 watts less than the other. How would you, I know me, if I got approached by my customer and said, Craig, you just approved a fixture that's 67 watts more. I could have had the other one for virtually the same price. Why did you do this? Well, the old way of thinking, you can't think that way anymore. You just need to pull it out of the grain and throw it away. You cannot use ISO traces anymore as a lighting designer and architect to design an application. You can't do it. You have to do a software layout, and you have to look at what those minimum foot candles are and the max to min ratios. You just can't call this as an equal. It happens all the time. I mean, you get close to the end of the construct, right before a bid or whatever, and you get everybody in there trying to get approved equal and everything. This happens all the time. It can get you in trouble, a lot of trouble. Here's an application, in that same as a public application where we got published and our competitors did. So we got to see with them. In this case, 26 volts, 70 luminaires, 18,000 watts. And because of our tailored lighting distributions, 25 volts, 54 luminaires, we saved them a pole, 16 luminaires, and 4,000 watts. That's substantial. That customer opened their eyes up immediately and said, wow, this is really the direction we need to go because I need to make my carbon footprint smaller in all my projects. Now here's another one. This is a garage lighter. Normally when you go indoors with a product, you kind of want a distribution that's a little bit wider. And you got to be really careful there on looking at over-delivering. In this case here, has anybody heard the new bug ratings? Anybody work with them? Everybody understand that? In this case here, you're looking at a fixture on the left that virtually is, putting out the same amount of lumens, but it's in a complete different glare rating, G rating, one higher than the other. But again, you could be fooled by this because that's the half foot candle trace between both of them, and they're identical at the half foot candle. It's out beyond that half foot candle where things start to really fall apart, and you need to be very careful as a lighting designer. So this picture here, this is the first time I've showed this, and I struggled with this a little bit. I started to question myself. For the last 35 years I've spent as an architect and as owning my own companies. I owned a foundry that we built chandeliers, and that went so well. We started building architectural gates and iron and stuff. And we strive so hard to create architecture to blend with other architecture. And I struggle to find myself, these look like they're unfinished. It's like they're missing the rest of the light fixture. But it's the way that they're delivering like a fixture for $25. But, I can't understand that an architect or an engineer would go, yeah, that'd be fine on my $300 million building. I struggle with this, and I looked at the amount of fixtures, and I'm like, wow, I'm really baffled with that. And that's how much this technology has changed architecture and lighting. It has driven us to the point to where, so the manufacturer seems to think that the owners don't care, or people don't care what that architecture looks like. But I think that's not correct. I think that architects are still architects, lighting designers are designers. And I think at the end of the day, although we need to get there in price, the price is really there now with the products. They're down and they make sense with LEDs and even indoor and outdoor products. That there's no reason to sacrifice aesthetics on products that look like that. You know, and you know, when, and it's cut off up there, but you know, when is the technology ready? Just like the other picture, I still see this. I get fixtures all the time. You know, our reps bring in and go, Craig, take a look at that one. You know, and it's just a box with LEDs in it. You know, and I ask them, are they really selling it? You know, and you wonder about that. You know, but you see it every day, and you know, I don't understand it. But they're there. We got to be very careful with them. Because as an owner, as a designer, and also as a manufacturer, we don't want to warranty that. I mean, people are asking us for 2 years, 5 years, 10-year warranties on things, and you know, I'm not going to deliver a light fixture to this, and I'm not going to sell a warranty with it. There's no way. I mean, Acuity brands want to sell you a light fixture, and you're going to keep it for a lifetime. We've spent a lot of time developing the architecture to make it simple and sleek, and one of the things that I just noticed now as we start to see these light fixtures being put up on poles outdoors is that now the pole looks too big. I mean, we were used to 4-inch and 5-inch, 6-inch light poles. We're putting a lighter fixture, lighter weight fixture, and a much thinner profile. You got to remember, we're looking at a fixture from a certain angle, like 60, 70 degrees. We're not looking at this big HID fixture that's got foot depth and girth and height. We're looking at a fixture only 4 inches. Now all of a sudden the pole looks too big. So as a specifier, you got to wind up or back up a little bit and go, really, what diameter pole do I need with this new technology as well? Ask yourself that. And look at it. Don't just assume that that's what I've been doing. I specified a 4-inch pole, or I spec'd a 6-inch pole. That's what I did. But you really don't need to do that anymore. There's other alternatives to really, and as that technology becomes thinner and lighter, it blends with the architecture. It's what I call illuminated architecture. And that's it. Any other questions? Sure. So, you know, kinetic flash, maybe not Einstein type term, but the guys in my department like it. It could be the strobing effect, right? So, pardon?
I was wondering, is it the chips as you ride by? Do you
So
see
it's
flash?
It's the optics. So, and you'll see with optics that only do a certain job, and then there's an optic next to it doing another job. As you transition from one point to another, you go from one optic to the other, and you'll get a flash. Now, if they didn't do a good job at blending those two flashes together, here's a really good example. There's this lighting manufacturer not us, that decided to light a super speedway, a big racetrack, right? And you know, they spent all this development time, and they went out there and they put the fixtures at 20 feet on center down straightaways. They didn't think that these cars were going 200 miles per hour. And the drivers were going down there, and it was like flashing inside the car like crazy. That's exactly what's happening with this kinetic flash. So that other manufacturer had to come by and you had to eat that project and put them at 3 foot on center, right? That's that overlap part, right? So that the drivers didn't complain. So that's what they do now. I mean, they lit all of the racetracks now, and they're like 3 and 4 foot on center. Huge. I mean, it's a huge lighting project. But anyway, that's really, you know, what we say is kinetic flash. You know, we see it as a problem. One of our big customers out west definitely have dealt with it, and they do not want to do that anymore. And they no longer use those manufacturers that do that because there was concern about epileptic seizures with flash strobing lights and stuff like that. And as soon as somebody said that, I just, no, I don't want to do that.
Any other questions?
Yeah.
Have you noticed anything from the auto industry now that might inform new LED design or how it relates to architecture?
Yeah, so the automotive industry is, they're still out there ahead of us, for sure. I'm working still with one of them right now on an architectural custom installation for them. But there are huge developments in materials. So what you're going to see in the future, what I said earlier about some things that are going to be really cool in a couple of years, is like no more aluminum, right? And becoming green and 100% recyclable, non-serviceable. In other words, light fixtures that potentially can be just bolted onto a pole or bolted onto a building, and you walk away from it when it burns out. The cost is low enough to where you replace it. And when you replace it, like brake lines in the fixture, where you break the fixture, take the circuit boards out, and you 100% recycle that process. Those are the kind of things that LEEDs and Title 24 are driving us to, and my innovation team is looking at. And the automotive industry, they're there. They're using composites. When I was up at one of their facilities the other day, because of the light fixture we're designing for them, I was in their R&D facility looking at 2016 vehicles where like the entire engine except for the block in the head was all plastic, and the radiator all plastic, everything is just composite, and when they get done with it, they grind it up into chips and make carpet out of it. So, yeah.
Any other questions?
Yes.
Okay.
Hi. Building on one of your slides with is the technology ready. I see LED suppliers working a lot to prevent failures and to avoid damaging the reputation of the technology. So what kind of failures are you seeing in the field, and what are you doing to avoid them?
Well, I mean, when new technology emerges, there's always bumps in the road, right? And you quickly validate them and you move forward. There's two categories, the way I would explain that, right? You've got the tier one luminaire manufacturers that spend enough time in product development where they vet out a lot of this stuff before we launch it. I mean, I've got fixtures designed that will probably never get built, but they're pretty sci-fi, and they're, but we're using that technology to understand how we get down the range. Now, this guy here, he probably doesn't have that R&D department and everything. And we are seeing huge failures. I mean, entire companies being swallowed up in lawsuits because they sold 10,000 of these light fixtures on a job, and now they're asking us to bid it with another product, and somebody's going to pay for that. That's what they're pointing at. That's the kind of thing that we weigh as a company. We are not going to position ourselves that at a high risk where we deliver or over-deliver technology to where it comes back and bites us. But we see it, and some of the tier one light manufacturers really don't dabble in that market. You're looking at tier two and tier three lighting manufacturers that can only afford to do this. Did that answer your question?
Yes.
Okay, any last questions? We'll take one more. Okay, well, thank you all so much for joining us. Let's give a big round of applause. Thank you so much anybody has extra questions. We encourage you to check out the deck a little bit. We'll stay, we'll keep the party going for a little bit longer. Thank you all so much for joining us.